Hi, I'm Ben Greenstein. I work at Google in Seattle, in the United States of America. And I'm presenting a topic preview on edge computing. So before I begin, I just want to mention that these slides are my take on edge computing, not Google's take on edge computing. So please don't mix up the two. This isn't any official statement, company statement. This is my opinion. I'd also like to say that many of these slides were inspired by, borrowed from, or flat out stolen from Satya over at CMU and Victor Ball over at Microsoft Research. Okay, so I think the best place to begin when trying to introduce the topic of edge computing is to discuss the cloud and why the cloud is so great. The centralized infrastructure of the cloud makes it easy for anyone to deploy software, to deploy a service, to update that service, and to manage new services. And those services can be really anything. They can support arbitrarily sophisticated processing and sophisticated machine intelligence. So the cloud's pretty great that way. And what the cloud has enabled is for us to take reasonably dumb clients and provide amazing experiences for them. Maybe the simplest version of this is the query response structure of the web. So a dumb client, like a phone, can ask for something like, say, hey, why is the sky blue? And that's sent to the cloud. And then the cloud thinks about it. And then eventually the cloud answers, well, the sky is blue because a clear, cloudless daytime sky is blue because molecules in the air scatter blue light from the sun more than they scatter red light. There you have it, the answer. This seems pretty great, right? We can get any answer from the web. We can get any answer from the cloud. There's some fundamental issues with this setup. Okay, so the first one is this number. Speed of light, yes. So the request from that phone has to make its way to some distant server, possibly across the world. Okay, so this is a map of submarine internet cables. And so let's say you want to you live in Botswana, which is in southern Africa, and you want to make a request to hit that's being served by a cloud server in, say, Atlanta, Georgia, in the United States. Well, it's going to be about 8,000 kilometers to get from Botswana to Europe. And then you're going to have to hop over the Atlantic and go maybe another 7,000 kilometers to get to Atlanta. That's a non-negligible amount of time traveling at the speed of light. The round trip is about 100 milliseconds. Note Nigeria, which is a very populous country in Africa, also has round trips to places like Atlanta in that range, in that ballpark. Okay, but that doesn't seem so bad. It's 100 milliseconds. Well, another problem is that the internet is complicated. The internet is a collection of autonomous systems managed by ISPs with complex peering relationships. So your request and the response are going through a number of different hops across different ASs. And it's being packetized, and those packets are queuing up in various servers, and those packets drain out of those queues. And over time, and that adds additional latency, potentially at each hop. Making matters worse, that cellular device is attached, that mobile device is attached via a cellular network. And so there are additional latencies in making your way through this mess, including, and probably most notably, just establishing a connection with a base station can take some time. Okay, put this all together, and this is what you have. This is a histogram. This is Chrome metrics. We call this Chrome UMA, or user metrics analysis. And the way to read this is on the x-axis is around transport latency, and on the y-axis is the number of samples that had that latency. And it paints a pretty dark picture for Nigeria. On the far left side, we see that less than 1% of the samples taken have round trips that are under 40 milliseconds. I would think 40 milliseconds is like the bare minimum for a reasonable round trip time. 10%, only 10% are less than 100 milliseconds. The median here is 250 milliseconds, a quarter second for a single round trip. And what's really horrific is if you look over at the right side of the distribution, 5% of these samples are over 1.5 seconds each. Making matters worse, to make that request to the cloud and get a response isn't just a single round trip. There's a round trip for the TCP handshake in the case of the web, in the case of HTTP. Then there's typically two round trips to set up a TLS connection. That's with TLS 1.2. 1.3 reduces that by one round trip, but it's not widely deployed yet. And then we add another round trip for the HTTP request. So put that all together, that's about 4 round trips. So remember I said the median in Nigeria transport round trip time is 250 milliseconds. So you'd expect the median HTTP round trip time to be about a full second. And that's exactly what it is. So a metric that we use in the browser world is something called navigation to parse start. That's when the user tries to navigate somewhere, the time from that point to the time when the first byte of the response is received. So in Nigeria, the median is 1 second to that first byte. And that's not receiving the whole web page, that's just the first byte. At the 95th percentile, it's 10 seconds. Globally, the median is 600 milliseconds and 3.5 seconds at the 95th percentile. Okay, so if that weren't enough, the world's gotten more complicated than a simple client response setting with the web and a thin device. People are thinking about streaming video for virtual reality and augmented reality applications. And there, humans' latency sensitivities are measured in the small tens of milliseconds. Likewise, people are thinking about streaming video games, interactive video games. Again, latencies in the perceived latencies in the small numbers of tens of milliseconds. People are also thinking about using IoT devices for sensors and security systems, for IoT sensors for climate and security systems. And maybe most notably, people are now very actively processing video and audio for a host of different applications. Okay, so let's talk about video for a little bit. If you have a 1080p camera, that typically uses about 10 megabits per second to upload. If you have 4K video, or if you look at the downlink, Amazon and Netflix both say that it ranges in somewhere in the range of 15 to 25 megabits per second that you need for a single stream. The Nest Cam IQ says it uses anywhere between 100 and 400 gigabytes per month to stream this data. So that seems doable, if you have an application that has one camera. But these days, people are thinking about, larger applications that have thousands of cameras that are in use. And so if you multiply any of these numbers by 1,000, you quickly see that it becomes either flat out impossible to stream that much data, or so cost prohibitive you wouldn't want to do it. Making matters more complicated, privacy has always been a concern and has very recently become a very significant concern. The risk is that basically, if you have these cameras, say in a security system, pointed at you all day long, then you might do something that you don't want other people to see, and that's streamed up to the cloud and stored for all eternity. So if you search for internet privacy or cloud privacy or video analytics privacy in the news, you'll see lots of stories every day. And the larger companies have gotten very serious about trying to figure out ways to protect privacy. Tim Cook at Apple, you might say, has been leading the charge, saying things like AI must respect human values, including privacy. Okay, so up to edge computing. So edge computing to the rescue, right? So what is edge computing? I'll use Satya's definition first. It's computing and storage nodes are placed at the internet's edge in close proximity to mobile devices and sensors. There are a bunch of definitions out there. Another one is edge computing is the practice of processing data near the edge of your network where the data is being generated instead of a centralized data processing warehouse. If you want a few more buzzwords, edge computing is a distributed computing paradigm in which computation is largely and completely performed on distributed device nodes known as smart devices or edge devices, as opposed to primarily taking place in a centralized cloud environment. In a nutshell, the edge computing is really about taking the computation that was in the cloud and pushing it closer to the end user devices, to the mobiles and to the IoT devices. Okay, so why is edge computing so valuable? I've said this, but I'll summarize. By the way, these four aspects are from the emergence of edge computing that Satya wrote back in actually only last year. So it provides better latency. So now it enables like highly responsible cloud services because you don't have to go all the way to Atlanta from Botswana. It reduces bandwidth requirements significantly on the backhaul to the cloud. And you can do significant analytics on IoT sensing. As I mentioned, it can provide privacy because it can act as a firewall between raw sensor producers, or raw sensor data producers, and the cloud. And one thing I didn't mention, but I think is worth noting, is that it can make services more available. There are lots of reasons why cloud computing can become unavailable at times. There can be network disconnections, or sometimes cloud services go down. This provides like a layer of redundancy there, so that you can continue running your service even when the cloud is unreachable. Okay, really quick history on edge computing. So I think it started with content distribution networks in the 90s. So Akamai deployed CDM. And so a CDM, basically the idea is you put caches closer to the users, so the round trips are shorter. You can think of edge computing as a generalization of that. So you're putting computation as well as caching close to the user. And then at the same time, like maybe from the 90s, or actually probably before the 90s, but I maybe started tracking in the 90s, through to today, there have been lots of papers on computation offload. So the idea of like taking some of the workload of a client device and putting it in a server. So Odyssey was a famous paper from SOSP in 1997 that looked at having OS support for reducing fidelity, application fidelity in response to like various system constraints, such as like networking constraints. I'll mention one paper I wrote back in 2004, Tenet. There we were looking at sensor networking, so we had thousands of sensor devices, and at the time we were all thinking about streaming all of that data back to some cloud, and it just seemed untenable. So we instead built a hierarchy where we put another, like basically an edge node that could process that data and filter it and distill it and then forward the result onto the cloud. And Mali is a paper more recently in MobiSys 2010 that was about figuring out the best way to distribute code for an application across client and server. Okay, so that was going on. Separately, I'm sure you're all aware, cloud computing emerged like in the 2000s, roughly. And in 2009, Satya and Victor Barr and Ramon Caceres and Nigel Davies wrote this paper for Pervasive where they articulated the notion of cloudlets. So cloudlets are the academic notion of, or the initial notion of edge computing. And then around 2015 or so, industry got really excited about this term edge computing. And so you see it in lots of products put out by the big companies as well as marketing literature. So more history since that cloudlets paper. So Nokia and IBM put together what they call the Radio Applications Cloud Server. which was acclaimed to be like the first mobile edge computing platform. The ETSI, the European Telecommunications Standard Institute, began standardization efforts around edge computing. Vodafone, Intel, and others started the Open Edge Computing Initiative in 2015. The Mobile Edge Computing Congress was formed in 2015 and is still operational. The Open FOG Consortium, get it, FOG? It's not the cloud, but it's close to the user, so it's the FOG. Consortium was created by Cisco, Microsoft, and others in 2015. A conference was started all about edge computing, the Symposium on Edge Computing. It started in 2016. The most recent one was just last week. And there have been plenty of research projects. The Elijah and Gabriel at CMU are about cloud computing and wearable cognitive assistant using cloudlets. Okay, so I'll talk about the academic notion of edge computing, and then talk a little bit about the industrial notion of it. So the academic notion started with the term cloudlets. And so the idea was that this is a small data center at the edge of the internet. It could come in many sizes and forms. It could be like an actual server that's sitting near end users, or it could be an access point that has a spare CPU. A defining part of the definition was that it had only a single wireless hop from the mobile device, plus maybe a fiber connection or LAN connection. But not a multi-hop network. It's multi-tenant, as in the cloud, meaning you can have multiple users or multiple applications running. Provides good isolation and safety. So the initial conception was that this would be VM-based, so you'd have a guest VM. But this is obviously extensible to like lighter weight ideas like containers, like the Docker containers, or even Lambda functions. It doesn't. So also importantly, edge computing doesn't have cloudlets don't have the constraints of the mobile devices. Things like energy. It's assumed that there's a power source, and form factor. It's assumed that if this thing processes like crazy, it's not going to overheat. Important to note, though, is that this notion of a cloudlet is something that's separate from the mobile device or from the IoT device, and separate from the cloud. It's something in between. Okay, in industry, the first notion of edge computing extended data centers. So I'll just pick on Google for a little because I work for the company. So Google operates data centers for computation and backend storage in the Americas, in Europe, and in Asia. And so it might be hard to see, but there are a bunch of dots there. Those are each Google data centers. So naturally, an extension of this would be to add edge nodes. And so network operators and ISPs deploy Google-supplied servers inside their networks. We call this Google Global Cache. And there are many, many dots. I'm not sure if it's public how many dots exactly there are. And so the idea first was that these are basically like a CDN. Static content, including like YouTube videos or Google Play, Google Play binaries, are temporarily cached on edge nodes. And then Google's traffic management system directs user requests to edge nodes that will provide the best experience. But in some locations, we're now using edge nodes to support the delivery of other Google services, like Google Search. So that's computation, suddenly, where in ways that it provides the best end-to-end, or the best experience to users. Okay. Another notion that's come out of industry is one where the devices aren't like an extension of the cloud infrastructure, but are instead part of the customer infrastructure. And so Azure Iot Edge is one of, basically Microsoft, Amazon, and Google, and maybe others all have solutions in this space. This is one of these platforms that makes it easier to involve edge computing, compute power in your applications. AWS Greengrass is Amazon's version of this. And it's very, very similar in goals, a little bit different in how it's actually put together. For time, I'm not going to go into details on these. And then Google has yet another. And for some reason, they all talk about oil rigs, but as one application. And so all three of these are extending the cloud to the edge and providing tools to make that easy. One bit of work I will talk about related to this is federated learning. And this is an area of research, and it's also an area that industry is very excited about. So the idea of federated learning is that you can put together a machine learning model without pulling all your training data up to a cloud. And so just very quickly, the way this works is the cloud has some initial model that it will send down to a bunch of edge nodes. And the edge nodes will use like local raw sensor data as label data to try to improve on that model. And we'll make slight adjustments to that model, upload the model again, and the cloud will then take all of those like deltas on the initial model, kind of average them in some way to come up with a new model, and in the process having improved the model, and then that process repeats. And so the whole gist of this larger project is that ML is great, but sharing your personal sensor data with the cloud is not so great. And I think this is a really interesting promise of edge computing, particularly in the current tech climate. Okay, so I should talk about applications. Maybe, like some people have said that this is the killer application, video analytics, because there's a lot of data. It's like too much to send back to the cloud, and there are real privacy concerns. So Glimpse was one project in this space that did real-time object recognition on mobile devices. This is work done by MIT and Microsoft Research, published at Census in 2014. Another project in this space is called Vigil. This was in MobiCom 2015. And this is about the design and implementation of a wireless video surveillance system that uses edge nodes to basically to do the video analytics. Another application area is augmented reality. So this is some marketing for Google Lens. The issue here is that augmented reality is CPU intensive and latency sensitive. And so we're limited on a mobile device in what we can do in real time. So obviously having an edge node could extend that. Another area that people are interested in is health sensing and analytics. Two people from our community, Deepak and Prashant, have this new mobile health sensing and analytics laboratory. And so they're analyzing lots of sensor data in this space. Privacy is a huge concern in basically all medical applications. And so edge computing can help in that regard. Vehicle-to-vehicle communications and intra-vehicle applications are another area. If you think about it, if you want to have a system that can help avoid crashes by sensing that two cars are coming close to each other, you don't want to route that information up to the cloud and back down. You'd never get it there in time. So having some edge node, maybe it's in one of the cars or the other or next to the car, would help reduce latency. And if you think about it, self-driving cars are kind of like the ultimate example of edge computing. They're collecting tons and tons of data, and there's some node in the car that's figuring out what it needs to actually actuate systems in the car, at the same time sending some data back to some cloud for further analysis and tracking. Smart security systems are another area that people are interested in for edge computing, largely for privacy reasons. You can keep your sensor data in your home. And just like self-driving cars, aircraft sensor analytics are an area where edge computing is important. I saw, I forget which paper it was, but someone cited that a flight uses creates about a half terabyte of data. And so shipping that off to the cloud for analysis seems like too much. Okay, so all this brings us to why as a bunch of researchers should we care about this at all? Isn't it all solved? Isn't industry they already have applications? It must be done. There must be nothing left to publish on this topic. It's a topic that's been around for a decade. So maybe we're done. Turns out there's still plenty left to do here. So I'll just go through this briefly. So in terms of security, well, how do we keep data secure? Provide integrity, confidentiality, and authenticity with an edge node that's potentially in a different trust domain than from the client or from the cloud. And then how do we manage the physical security of these edge nodes? I mean, if you think about a data center has potentially even like armed guards or guards, plus locks and walls. What does an edge node have? How do we architect multi-tenant edge nodes that isolate various clients from each other? On privacy, how do we ensure that sensitive data is filtered appropriately in these edge nodes before forwarding it off to the cloud? How do we keep edge nodes up and running and connected to end user devices and to the cloud? How do devices connect to the nodes? How are the edge devices connected to the cloud? How do we find edge nodes and decide which edge nodes get a client's workload? How do we balance these workloads over the cloud, the edge, and IoT or mobile devices? How do we support more devices when lots of devices are trying to use these edge nodes? Tomorrow, in the first session, there's a paper called Foggy Cache. And the idea there is to try to eliminate redundant computation in these edge nodes. So look out for it. And how do we hand off workloads across edge nodes? How do we deploy edge nodes and manage them? Another paper tomorrow is on using UAVs to deploy LTE base stations. But deployment is also a challenge on automobiles, in retail, on factory floors, in homes, and in enterprise. What's the right hardware architecture or software architecture for an edge node? What are the right programming models? What's the right API? Will there be generic ML libraries in these edge nodes, or are they going to be tailored to very specific applications? And finally, who's going to pay for all this? What are the right business models? All of these problems are still largely unsolved, but there's great potential here. So I'm going to close with a slide. This is from a Gartner report that says the edge will eat the cloud. It's like maybe a little bit sensational, but one quote in it is 40% of large enterprises will be integrating edge computing principles into their 2021 projects, up from less than 1% in 2017. This edge computing is real. The large companies all have big initiatives around this. It's not going away, and there are tons of problems to solve. So it's a call to start conducting research and writing papers. So that's all I have. So thanks.